In this lesson, we'll be applying the ideal gas law to solve problems in ways that don't just use the PV equals nRT equation. We're using some derivatives of those equations and moving on then to help you figure out how to choose a gas law equation, not just the ideal gas law equation, to solve gas law problems. Alright, so the problem we're working on here is this one. What is the density of CO2 gas at 0.500 atmospheres and 27.0 degrees C? So there are a lot of ways to solve this. Density is going to be some kind of mass over some kind of volume. We could solve using the standard ideal gas law, and then you would end up with moles and a volume, and then you would use the molar mass of CO2 to convert to mass to get to mass over volume. So you could do that. You could do it as a two-step problem. All right? So it's not that you can't use PV equals nRT. You can. It's just that there's another version, this one right here, where my thumb is pointing to, another version of the ideal gas law that gets it a little more straightforward. So let's start off by making a list of what we know. We'll do a few calculations and add to the list of what we know, because we can figure out the molar weight or molar mass of CO2. We do have already, though, well, it's asking for density, so I'm going to put this up here as a question mark. Okay. We do have the pressure, 0.500 atmospheres. We do have temperature, 27.0 degrees C. But we all know by now, I hope, that you can't calculate gas law stuff with temperature in degrees C. We've got to get it into Kelvin. And so we want to go over here and calculate what the Kelvin temperature is. So 27.0 degrees C plus 273.15. And then we've got an empty slot over the 5 here. And the way that I teach you to handle significant digits for addition and subtraction like this, because we are adding, is anytime you have a digit resulting from an empty slot in addition or subtraction, that digit is insignificant, so we underline it. We draw an arrow to show a rounding off. And the amount or value of Kelvin that we're going to use is 300.2. So we'll say that's 300.2 K, and you don't have to, but I kind of tend to draw a line through that just to remind myself I don't want to use degrees C, I want to use Kelvin. Okay? All right. Now, what we can solve for here, we need to solve for the molar mass or molar weight of CO2. That's something that would help us here, because we do have a version of the ideal gas law where density is equal to molar mass times pressure divided by the ideal gas constant times Kelvin temperature, and so we need that molar weight or molar mass here. So let's see, do I have enough room to do it there? Maybe not. Let's just do it over on the side over here. So carbon is 12.01, oxygen is 16, and we've got 1 carbon, and we've got 2 oxygens. And we add it together, and we get 44.01. And there's no reason to round off over here because there's no empty slots to the right. And it's only empty slots to the right, not empty slots to the left that you round off. And so this is going to be grams of CO2 equals 1 mole of CO2. Okay? So the molar weight needs to be in a fraction, just like all the other conversion units we've ever done. Okay? You could put the grams over the moles, but what's going to make it easy for us here, if you got into the problem and couldn't cancel, you'd see you need to flip it over. But I would probably go ahead and write it as 44.01 grams of CO2 over 1 mole of CO2. Okay, so there's our molar weight. So we have everything we need. The only thing I haven't written down here, but we have it, is the ideal or universal gas constant. We need the universal gas constant that includes atmospheres, and this is the one that's on both sets of references, the homework references that this class uses and the AP chemistry references you use. The AP chemistry version just has one less significant digit, 0.0, 821 liters times atmospheres over Kelvin times moles. Okay? All right, so we have this density of a gas is equal to molar weight or molar mass times pressure over the gas constant times temperature. And so we're going to just simply start plugging all this stuff in now. Let's see. So we're going to have density equals molar weight times the pressure, 0.500 atmospheres. And to keep things well organized, I'm just going to put that over 1. And then all of that's going to go over the ideal gas constant, or the universal gas constant, 0.0821 liters times atmospheres over Kelvin times moles. Now, just a word of warning, I have students all the time that look at liters, atmospheres, Kelvin, and moles and think that you can plug values in there. These are measurement units here. They are not variables. These are variables, okay? These are not. These are measurement units. These are variables. You can plug stuff into this. You cannot plug stuff in for liters or atmosphere or Kelvin or moles, okay? All right, and then we also have temperature down here, and the temperature is 300.2 K, which I'm going to put it over 1 to keep everything well organized. Now, this is a complex fraction, and I know that you've been taught how to resolve a complex fraction before. Okay, and what you've been taught to do, and I shouldn't put a time sign, it should be an equal sign, is to invert and multiply. When I was in school, there was a famous epic poem, The Charge of the Light Brigade. A famous line from that famous poem was, "Ours is not to reason why, only to do or die." I believe that's quoted correctly, so we just took that and flipped that around to say ours is not to reason why, only to invert and multiply, to remember how to resolve a complex fraction, if that helps you. So 44.01 grams of CO2 over 1 mole of CO2 times 0.500 atmospheres over 1. Then I'm going to take everything that's on the bottom and flip it. That means, that's what I mean by invert, okay? So instead of Kelvin being on the bottom, it's now going to be on the top. Moles is also on the top. 0.0821 liters times atmospheres goes on the bottom. And then we're going to flip this one as well. Okay? And now we can start to cancel everything we can cancel. So CO2 can be canceled by CO2. Moles can be canceled by moles. Atmospheres can be canceled by atmospheres. Kelvin can be canceled by Kelvin. And the units of measurement I have left are grams, which measures mass, over liters, which measures volume. And density is mass over volume. And most of the time in gases, we use grams divided by liters. Okay, and that's what you should do. If you're grading somebody's paper, you should write down the steps. That is, if they didn't get every step in there, explain it to them. All right, that's your job if you're correcting their paper, because your job is to help them. All right, you want to help them make an A, and hopefully they're going to help you make an A. Right?
I did it, but I just wanted to make sure.
Okay, so it's always better to do all the steps. Okay, when you skip steps, maybe not you, but most of the time, in all the years I've been teaching, when students skip steps, that's when something gets missed, some little something gets left out. Staying well organized here and organizing things in a very clear fashion helps you not make the mistakes. Okay, so, and that's what you want to do. You want to try to get it right. Okay, if you've been doing this same calculation for years, you do it every other day or once a week and for years, then you might be able to skip steps. But if you're not doing it all the time, my recommendation is never skip any steps. Always write everything out and be very, very detailed in how you do it. Okay? When you get into a college math class, for example, you'll be expected to write proofs. Okay? And in proofs, every detail has to be there. or you haven't offered the necessary proof for your whatever it is you're writing a proof for. Okay? And it takes forever. Yeah. You might be 3 or 4 pages in the proof. Yeah. Okay. So, says the current college student who's doing this stuff right now. All right. So now we're just ready to plug in all the values into a calculator, and I've got my little simple calculator. You can use any calculator, but I'm just using this to show that any simple calculator, any simple scientific calculator will do the same thing. So 44.01. Oh, see, that's what happens with this thing. If I'm not careful about hitting that button, I won't do it but once. 44.01 times 0.500. Whoop, I didn't do it times. And then times 1 just gives me the same thing, so I'm not going to multiply by 1. I'm not going to divide by 1 and divide by 1, but I'm going to divide by this number. So I'm going to hit equals first, and then divide by this number. Hit equals again before I also divide by this number. Oop. Okay. And so this is all set equal to density. So I can say density then is equal to 0.89227,437. We've got units of grams over units of liters. Okay, that's what we have left. And that makes sense because that's mass over volume. Okay, and so that's, what is that called? Let's see, the reasonableness test. Okay, when you look at your work and you look at the number you have, you need to ask yourself, does that seem reasonable? Well, gas has a low density, so that makes sense. Okay, do the units of measurement make sense? Yeah, that makes sense. Okay, if you don't ask yourself, if you don't do a sort of mental check, a reasonableness test, you know, you could probably find an error if you just realize that doesn't seem reasonable to me. You see what I'm saying? So just always look for what we call the reasonableness test. Okay. All right. Now we're ready to round off. So I've got 4 digits in this number, and we're looking at all the measured and calculated numbers here because this is a multiplication division problem. So I've got 4 digits in this calculated number, 4 digits in this measured number, 4 digits in this 3 digits in this measured number, 3 significant digits in this calculated number. These leading zeros are not significant. 4 digits in this measured number. So of those measured and calculated numbers, there are 4 of them. The ones with the least digits are this one and this one. So we want our final answer to have the same number of digits as the measured or calculated number with the least digits. So like I said, leading zeros are not significant. 8 then is our first significant digit. 8, 9, 2 then are all of our significant digits. Underline everything else. Draw an arrow. And we're going to write 0.89. And in high school, at this school anyway, we have a number that's 5 or greater here. It's going to round this number up, 893 grams per liter. And this is applying to carbon dioxide. And we put a box around it to show that's our final answer. Period. And we're done. Any questions? So for this practice problem then, we can use the standard version of the ideal gas law, PV equals nRT. We'll have temperature, pressure, volume, grams. So what we would have to do is we would use this stuff, other stuff we'd have to find moles, and then we would use grams per mole to calculate molar weight. So you could do that. All right, but we also have that derived version of the ideal gas law that simply allows you to calculate it in more direct fashion. It's the same thing. It's just set up in a slightly different way, where molar weight is equal to mass times the gas constant times temperature in Kelvin over pressure times volume. So let's make our list of knowns and unknowns. We know the mass of this gas is 12.0 grams. We have a volume of 19.2 liters. We have STP. So the temperature then is going to be 0.00 degrees C, and that is 273.15 K. So we don't have to calculate that, all right? And I can keep that 5 on the end here because this is an absolute number, okay? It's like I can put as many zeros as I wanted to, all right? So I don't really have to calculate Kelvin. You could. It wouldn't hurt if you did. I wouldn't count, but you wouldn't get any points for it in this case, all right? But look, if you can't remember, do it anyway. That makes sense? All right? You can't go wrong by doing it. And then standard pressure is 1 atmosphere. Okay? All right. So in this equation here, I have, let's see, I have mass, and R we know, temperature I have, pressure and volume I have. So I got everything I need to find the molar weight. Okay? Now the version of R we want should match atmospheres. Okay? And that's 0.0821. Let's see, liters, atmosphere over Kelvin moles, right? Liters times atmospheres over Kelvin moles. Got it? So we got, we want to use the equation where we have molar weight. So we're trying to find molar weight is equal to mass times ideal gas constant times Kelvin temperature over pressure times volume. So we plug everything in then, and the mass is 12 grams. The volume is, R is 0.0821 liters times atmospheres over Kelvin times moles. And temperature is 273.15 K. I'm going to put these over 1 because I'm seeing that I'm going to need that. And I'm going to put that over pressure, which is 1 atmosphere. And I'll put that over 1 because I know this is going to be a complex fraction now. I need to flip, invert and multiply. And volume is 19.2. Okay? And since I have this complex fraction, the way that I teach everybody to solve this is to invert and multiply. So I'm going to put what's on the top down here, 12.0 grams over 1. The universal gas constant, 0.0821 liters times atmospheres over Kelvin times moles. And then 273.15 K over 1. And then on the bottom, I'm going to take both of these and flip them over and multiply them. And that's the way you resolve a complex fraction. So it's going to be 1 over 1.00 atmospheres and 1 over 19.2 liters. Okay? And we go through and cancel everything we can cancel. So liters gets canceled by liters. Atmospheres canceled by atmospheres. Kelvins canceled by Kelvin. And when I'm done, I'll have grams per mole. Well, that's what molar mass is. It's grams compared to moles, right? So that's what we're looking for, molar weight or molar mass. So when I do the math, I should have the molar weight of whatever this gas is. So 12.0 times 0.0821 times 273.15, then divided by 1, but dividing by 1 just gives us the same answer, right? If I divide by 1, I'll get the same thing, yes? So I can skip that step if I want to. Don't have to, but I can skip that step. And I'm going to divide by 19.2. And I get 14. Is that what you guys got? 14.0, 14.0? So this is the complete answer in grams per mole. Going to round it off to, let's see, of the measured and calculated numbers, I've got 3 digits. 3 digits, 5 digits, 3 digits, 3 digits. So we want 3 digits in our final answer. We want to match the final answer with the number of digits we have, the least digits of the measured and calculated numbers. So we got 14.0 grams per mole of unknown gas. All right?
Container that contains liquid nitrogen. Okay, liquid nitrogen is, like really super cold. This is nitrogen gas that has been liquefied. Okay, and so what they do to do that is you squeeze it down, you compress it, and you allow the temperature to equilibrate, and you squeeze it down some more, allow the temperature to equilibrate. Eventually, you get liquid nitrogen. Okay, so it's a simple process, although the equipment's kind of complex. But what I'm going to do is show you some things that have to do with about cold temperatures. So we're going to take some liquid nitrogen and we're going to put it in this little container. So this is called a dewar. This is also a dewar, although this is a better one. It's a larger one, obviously. I really don't need the gloves just to move it around to handle some of the cold stuff I do, but you can see what it looks like as I pour it here. So this stuff is boiling all the time because it's has a really low boiling temperature. So I'm just going to put a banana in there for a while and let it do its thing. In the meantime, while that's doing its thing, let's put a little bit of this liquid nitrogen here in this container so you can kind of see what it looks like. And you can see it's boiling, but it's boiling and it's really, really cold, even though it's boiling. And so it's constantly boiling off, and when you boil things, you get a gas, right? Make sense? So eventually, if I held it on there, it would explode. I'm not going to do that. Do it?
No, it'd take a while. Is this where you're going to put some crazy background music?
I could. So here we go. I've got a balloon filled with nitrogen gas. All right. Finger on top. I get caught in there. Go. That scare you? So we're going to get that really, really cold here in a minute. I've got another one of those containers back here. While we're freezing that banana. Put a little bit in here. And since I'm not using this anymore, I guess I can go ahead and take this loose and put this into that container and use up this liquid nitrogen I'm using here. Uh-oh. All right, let's see. Hmm?
He went through a bad breakup recently.
Yeah. Okay, let's see. Let's see how our banana's doing here. Yeah, it's doing pretty good. All right, let's put them on this, put this in there too. And so if you're ever short on hammers, you can always freeze a banana with liquid nitrogen, right?
I tried that before, it didn't work.
It didn't.
It was just a regular banana, but.
Oh, my goodness.
So if you ever run short on a knife and you need to cut up a banana for your cereal, there you go. All right, let's see here. I got one more thing to show you. Let's see. Where did I put that? I have another balloon up here somewhere. Here we go. There we go.
Do you have really good lungs?
Huh?
Do you have really good lungs?
Yes. You know, I need a larger container to pour this into, and I don't have a metal container I can grab hold of. Oh, I know. Hold on. All right, let's see how cold this stuff really is.
Is it gonna make the balloon pop?
You think? It's really cold. What do you think the balloon's going to do?
So you get small.
Yeah.
Because the pressure will decrease, which will make the volume decrease. Chemistry.
Looks like a Robinson egg.
Hmm?
So now it's expecting.
Now it's expanding, right? Okay. So what happens to the volume of the gas when you get it colder?
Decreases.
It decreases.
That's so cool.
Okay. So that's liquid nitrogen. Okay? And the main thing is that since we're in gases, is I want you to, at least as it relates to this unit, is I want you to understand that volumes of gases shrink when you get them colder, right? Which is, what law is that? Volume and temperature,
Oil.
Charles' law. Pressure and volume, that's Boyle's law, okay? So this is a demonstration of Charles' law, right? So,
Okay, this is liquid nitrogen.
Before you die.
I'm gonna stick banana in here. Sticking banana in liquid nitrogen. Are we? Well, that's it there. I'm gonna fill up this.
I have a feeling something's going to explode. I want to.
And you see that's boiling? balloon on there. And it blows up. And it can go all the way until it bursts, but I'm not doing that.
Sounded like glass.
See, like,
And then you can crush the banana. I don't know if I'll be able to blow this up though. No.
Well, you can have one of the students there do it because they got more hot air than you do, so we're good.
Someone looks up. Seriously.
I do too. Did you
how big do you want it?
Bigger than that. Yeah. That should be good.
You want to try?
Yeah.
Oh, that tastes good. I get it. Thank you. You're all so lazy. I know.
Can you guys do that? That's all.
Throw the nitrogen?
Do another flower.
Sure.
Okay. Great.
Should I throw it this way?
No, go around the front.
Hold up, hold up.
You got some more in there? Go ahead and do it again.
Going over here.
I can't throw it over there.
Why?
That's crazy. Look at it.